So now that we've gone over lines and started talking about lines in terms of vectors instead of just linear equations like in grade 9 and 10, now we're going to look at planes. So give a vector equation of the plane containing those 3 points. So a line is just a straight line in space. A plane now becomes a surface. So on this plane, I have 3 points. And it doesn't matter where they are, it'll be tilted because of the third dimension. I just want a visual representation of what is happening. So in order to define a plane, I need 2 lines. If I only have 1 line in space, I can't really define a surface. It could go anywhere. But as soon as I put a second line, now I have a surface created, and that's exactly what a plane is. It's a surface. So a plane needs a point, we have 3 to choose from, and 2 direction vectors. So by putting the points on here, I can see that if I connect them up, I can have 2 direction vectors. So I'm going to find vector u, which is going to be a direction vector, which is the vector AB from A to B, and I'm going to use backwards subtract to find that. So 2 subtract -1 is 3, -3 subtract 5 is -8, and 1 subtract 0 is 1. But remember, when it comes to direction, this direction vector could be any multiple of this one. This one can't be reduced. I'm going to use it as is, but I could use 6, -16, 2. But it's good to know because when you check your answers, you might not always have the same answer as the back of the book, but you still could be correct. So then, and I'm going to actually call that D1. I added a little 1 to my D. So vector V is going to be my second direction vector, which is the vector AC. And again, I'm going to backwards subtract to find it. 3 subtract -1 is 4. 2 subtract 5 is -3. And 7 subtract 0 is 7. And now they want the vector equation. So the vector equation is x, y, z, or r equals, now you always start with a point on the plane. I can pick any of these 3 points. It really doesn't matter which one. I'm going to pick A because it's the first one there. But again, if you're checking answers in the back of the book, be aware that you're still right if you have either of the other 2 points. Plus, now we need 2 parameters. Sometimes it's T and S. I'm going to use P and Q, not equals. That's a plus. P times one of my direction vectors plus Q times my second direction vector. So the difference between a line and a plane is that a line has 1 direction, a plane has 2 directions. And that would be my vector equation. So example 2. I have the equation of a plane, and I know it's a plane because I have 2 parameters and 2 directions, and they have a point, and they want to know, is this point 4, 5, -3 on this plane? So what I'm going to do is I'm going to take the x, the y, and the z from the point, so 4, 5, -3, and I'm going to set it equal to the x, the y, and the z from the plane. So the x is going to be 4 plus 3p minus 6q. The y is going to be 1 minus 2p plus 6q. And then -3 is going to be 6 plus p minus q. I'm going to solve these. Again, I have 3 equations with 2 variables. That means I'm going to pick 2. I've honed in on this one because I like this one right there. So p is going to be q minus 9. I brought the q to the other side and the 6 to the other side. I'm going to sub 4p over here. So I get 5 equals 1 minus 2 times q minus 9 plus 6q. So 5 equals 1 minus 2q plus 18 plus 6q. So 4q is going to equal, so that's 19, so -15. Make sure I've done everything right. So -2q plus 18 plus 6q. So that's going to be 19. 5 minus 19 is -14. So then q is going to be -7 over 2. If I reduce to lowest terms, I brought the 4 over and divided. And then I reduced. And then p is going to be q minus 9 equals p. So -7 over 2 minus 9. So that's going to be -7 over 2 minus 18 over 2. So p would be -25 over 2. Sorry, you can't see that. So I got a common denominator. So negative 9 became negative 18 over 2. And then I got my P and Q. But here's where I have to check to make sure that they work. So 4 equals 4 plus 3 times P, which is negative 25 over 2, minus 6 times Q, which is negative 7 over 2. So 4 equals 4 minus 75 over 2, plus 42 over 2, and that is not going to work because the 4's will cancel out and there's no way that those cancel out. So no, the point is not on the plane. If I got solutions for P and Q, I'm not liking my P and Q, so I'm wondering if I have made a minor error in somewhere. But if you get answers for P and Q and check them in the third one and it works, it means the line's on the plane. If you get answers for P and Q and check them in the third one and it doesn't work, it means that that point is not on the plane. Okay, so now we're given two lines. So I have my plane, and I have one line on it, which is going to be R1. You can add subscripts if you want to. Now, the problem with this, if these weren't parallel and I just had R2, I can pick either one to be my point, and I already have my direction. The problem is, if I look at these, that's times 2. So these are parallel lines. It's really hard. Well, you can't, in order to define a plane, you need two distinct directions. So I can't reuse this direction twice. But what I do have is point A on one line and point B on the other line. So I can use this as my U because it's the direction of the first one. And then my second one, V, which is going to be D2, I'm going to use as the vector AB. So I can use the 2 points to find a second direction, which is going to be 0 minus 4, which is negative 4, 4 minus 3, which is 1, and 2 minus 1, which is 1. So I'm going to use one of these. I'm probably going to use this one because it's the lowest one, and this one, and either one of those points. So my plane is going to be 4, 3, 1. I just grabbed the first point there, plus P times 1, 1, 2, plus Q times negative 4, 1, 1. So in order to define a plane with two directions, you need two distinct directions. If they're parallel, you can't use the same direction twice. But because I had 2 points, one on each line, I could use those points to come up with my second direction vector. Now we're going to take a look at scalar equations. And scalar equations are AX plus BY plus CZ plus D equal to 0, where ABC is the normal. So A says find the scalar equation of this plane. I have a point and I have two directions. So if I think about what's happening, there's my plane. I have direction 1 and direction 2 on the plane. My normal is going to come out of the plane and it's perpendicular to both of those. So that's my N. So N has to be perpendicular to both directions. So N is direction 1 cross direction 2. So this is my D1, this is my D2, and I'm going to find the cross product of them in order to get my normal vector. So I'm going to do the trick that we learned last unit. So 2, 0, negative 1, 2, 0, negative 1. I take the first vector and I write it out twice. Underneath it, I take the second vector, write it out twice, scratch off, and now I'm going to do my x's and my subtracting. 0 subtract negative 2 is 2. Negative 6 subtract 0 is negative 6. And 4 subtract 0 is 4. Now, you can use this as your n. I know eventually I'm going to have to reduce into lowest terms, so I actually always reduce this n vector because it doesn't matter if it's short or if it's long, it's still the normal vector. So if I go back up to scalar form, ABC comes from my normal. So I have 1x minus 3y plus 2z plus d equals 0. Now all I need to do is solve for d. But I have a point on the plane. So I'm going to sub that in for x, y, and z. So that gives me 3 minus 3 times 0 plus 2 times 2 plus d equals 0. So d is going to be negative 7. So I put 3 in for x, 0 in for y, 2 in for z, because that's the point on my plane, and I got d equal to negative 7. So the scalar equation of my plane is x minus 3y plus 2z minus 7 equals 0. If you would have worked with 2, negative 6, 4, you would have had 2x minus 6y plus 8z minus 14. You would have gotten that equal to negative 14, but then we have to always reduce scalar form into its lowest terms. So because everything would have been divisible by 2, I would have divided to get it here. So I find by reducing ahead of time, it saves some work. So part B of that asked, is this the same plane? Because I can have an infinite number of vector equations for planes, because there's an infinite number of choices for our point. There's also an infinite number of choices for our direction, because if I look at my diagram, I could define a point there and use those as my directions. So there's not a unique or one final answer for the vector equation, but they will all always reduce down to the same scalar equation if they're the same. So I'm going to find the scalar equation of this. So I'm going to do n. The normal of the second plane is 5, 3, 2 cross 2, 4, 5. So 5, 3, 2, 5, 3, 2, 4, 5, 2, 4, 5. And a cross out. And I'm going to get 15 minus 8, which is 7. 4 minus 10, which is negative 6, and 20 minus 6 is 14. So just make sure I did that right. 5, 3, 2, 5, 3, 2, 2, 4, 5, 2, 4, 5. 15 minus 8 is 7. 4 minus 25. There we go. 4 minus 25 is negative 21, and that will work, and now it's right. What I was doing is, because I know it's the same plane, I know I have to get a multiple of the normal, so I was thrown off a little bit because this was not working, and that's why I knew to kind of go back and check. So now the equation of our plane starts out as 7x minus 21y plus 14z. Then we have plus d equals 0. I'm going to go back and grab that point and use that as my x, y, and z to solve for d. So 7 times negative 1 minus 21 times negative 2 plus 14 times 1 plus d equals 0. So negative 7 plus 42 plus 14 plus d equals 0. So d equals negative 49. So then that gives me 7x minus 21 plus 14z minus 49 equals 0. But this is not considered scalar form because it's reducible. 21. I can divide everything by 7 to get x minus 3y plus 2z minus 7 equals 0. And if we go back to our answer from question A, it's the exact same plane. So therefore it is the same plane because it has the same scalar equation. A plane can have many different vector equations, but there can only be one scalar equation. So now, find the distance from a point to a plane. We looked at in a previous video how to find the distance from a point to a line, and we developed the formula. The formula developed for this is very similar. It uses projection, but I'm not going to work through it. What I have is my plane, and I have my point up here that's separate from my plane, and then I have my distance. And that's what I'm looking for right there. So the distance is going to be the projection of, if I have points on here, this vector onto the n. We're not going to work through it all again. We're going to use the distance formula. So it's ax1 plus by1 plus cz1 plus d all over the square root of a squared plus b squared plus c squared. So it's the exact same formula as distance from a point to a line, but it's been extended to include the fact that we're talking about a plane and we have the third dimension. This is my x1, y1, z1. There's my a, b, c, and d, and I'm just going to fill in. So it's the absolute value of 3 times 0 plus 2 times -1 plus 2 -1 times 2 plus 6 over the root of 3 squared plus 2 squared minus 1 squared. So all I did there was fill in. So that's going to be 0. So I have -2 and -2, which is -4, and 6, which is 2, and the absolute value of that is 2. This is going to be the root of 9 plus 1 is 10 over root 14. So when I do the top, I end up with 2. When I do the bottom, I end up with root 14. You're not allowed to leave roots on the bottom, so I multiply by 1, which is root 14 over root 14, which gives me 2 root 14 over 14, or root 14 over 7. So the development for this formula is very similar to the development I did before. We use projections, but from here, we're just going to use that formula to find distance from a point to a plane.